I'd like to introduce our first speaker today, Marty Edwards. Marty Edwards is well known in the control system community. If you don't know him, please get to know him. He currently works right now as the, got to make sure I get the titles right because he's got two positions now, Managing Director of the Automation Federation and the Director of Strategic Initiatives at ISA. But I think the thing he's most known for is being the longest served Director of ICS-CERT, which we all know. So I'm going to give it over to Marty.
Thanks, man. Thanks, Mike. What a great turnout. This is fantastic. I couldn't believe when Dale asked me to do this, and now we're over capacity. Well, I'm going to go fast because I have about 200 slides and 45 minutes to do them all in. And unlike most of my usual talks where I talk about what to do to fix some of the security issues in the control system arena, my job today is just to bring you up to speed on what are the different sort of manifestations of control systems. What are the differences between those? Why do you need to understand at a pretty detailed level what the system actually does to be able to understand how to calculate the risk that the different cyber components have, right? So not a general security overview. So first of all, there's enough acronyms in the control system business to even get a government guy like me confused, right? Because governments love acronyms. So you'll hear terms like DCS, distributed control system. You'll hear terms like PLC, programmable logic controller, SCADA, supervisory control and data acquisition. You know, in the ICS-CERT, I kind of lumped all that stuff into the general ICS category. And there's some that dispute that that's not the best way to go, especially if you're trying to figure out how to granularly make a scale for risk, right? You could have a system that's just monitoring something versus a safety instrumented system that's doing some pretty significant and important control. We need to be able to communicate that in documents, right? We need to be able to communicate that as we go through. You know, and automation isn't new, right? Automation has been around for a long time. I think the underlying element here is that we're trying to automate, take humans out of the loop or make the human load less of a physical process. You know, that's the difference between some of the IoT type of implementations. You know, there's actually some sort of physical, whether it's a factory or a manufacturing floor or a water treatment plant, there's something physical behind it. That's the key underlier when you talk about automation and ICS. So there recently, in the last probably 5 years, has been the increase in the term of operational technology, right? Which actually I think makes a lot of sense when you look at how information technology or IT on the business side of the house, then we've got operational technologies or OT that are down in the plant floor, right? These are the systems that run the operations. This is a good term to be able to be that all-encompassing term, right? So I've seen people use the term OT as it relates to things like medical devices. I mean, that was one of the things that that my old team sort of took under their wing because there really wasn't a great place to report vulnerabilities in the medical devices. But they're certainly critical. You know, and you can think of a small insulin pump very similar to, you know, a dosage pump that's pumping, water disinfectant in a water treatment system, right? Very similar, just different scales. And again, how they're applied is how you're going to have to calculate the risk of these systems, right? What's even more interesting to me is that if you look at the code in some of these medical devices, and you look at the code in some of the sort of legacy industrial control system devices, they're remarkably similar. They were built by 3 guys in their garage and in the 70s, and they've ported the code from processor to processor to processor, and they haven't fixed anything. So target-rich environment from a research perspective, right? I mentioned that control systems and industrial control has been around for a long time. You know, when I started in the 80s in school, I mean, one of the things we got trained on was pneumatic controls, right? So you would go out, a sensor, a temperature sensor or a pressure sensor would actually send an air pressure signal down a little tube that went to the control room. You'd have a controller that read that air pressure in, and through a lot of mechanics would adjust the air pressure that was headed out to a valve. And I'll tell you, when you looked at some of the tubing installations in big installations, they were like a sculpture. Thousands of stainless steel tubes all coming into a central area and all going back out. We tuned those just like proportional integral derivative PID controllers, right? They had settings, they had set points, they had changes. You could put them in manual, take over the valve, you could put it in automatic. So all these terms that we use in the control system community aren't just because of the computerization or the modernization in electronics, right? These terms have come with us for decades. And instrument engineers, as they were called, you know, knew how to set all these systems up and keep them running, right? This is an actual picture I took. I came out of the pulp and paper industry. So when I, you know, got into the mid-career, I would say, standalone electronics were kind of the thing. So we took those standalone pneumatic controllers, converted them to electronics. Now you have basically a sensor in the field that has a twisted pair wire connecting it to this controller, this control panel, and then you have another twisted pair wire that goes out to the control valve to manipulate the flow. So if you're controlling flow, you've got a sensor that's measuring something like the differential pressure across an orifice plate, sending back that signal, and then the operator interfaced with it through these types of standalone controls. No networks, right? Interesting thing when you talk about network evolution, I guess I was lucky enough to be in industry when some of the very first networks started to show up. And often the control system area was one of the areas that got the very first, you know, electronic network to connect things together. There were usually two pieces of a business that had that kind of networked automation. One was the industrial control system area, and one was finance or warehousing, right? They wanted to keep track of what was in the warehouse. They wanted to send bills and invoices. So you had big blue AS400s on one side doing all the finance stuff, and the company I worked for, it was all VAX VMS based on the control system side. So this panel that I show here has both analog controls and digital controls, right? So the push buttons, start and stop motors. You could have hardwired interlocks or logic behind that. Very, very challenging to troubleshoot, very challenging to maintain. So here's some of these first networks, right? Lots of serial. So RS-232, RS-485, multi-drop, a lot of different serial communications implementations. If I looked in one of my old technician bags, I probably still have a breakout box that looks like that to break out the pins. So you would basically look at the data that's going back and forth between these devices and try to figure out why they wouldn't communicate. And often in the networking area that I was responsible for, just getting the thing to talk was success, right? We weren't worried about how robust it was. It talks. Leave it alone. There's a wire hanging out of the the DB9 or DB25 hood that's plugged in, and there's a wire hanging out there. Whatever you do, don't touch it, because if you touch it, then it stops talking. We don't know why, but it stops talking. And some of the first jobs, Eric Byers is here somewhere. One of the first jobs Eric Byers sent me out on to do network troubleshooting was to troubleshoot communication between programmable logic controllers that were at the opposite end of a big pulp mill. Thousands of feet of cable between these two programmable logic controllers, and the mill was having trouble with that communication. And literally, you took your little toolbox and you walked, and every couple hundred feet there was a little gray box somewhere where the twisted pair connected and another device connected to it. And we found all sorts of things. You find cables that have been run over and smashed, and they're literally flat, and the wires are hanging out of them. You find insects that have taken over. You find rodents that have chewed through them. That was that was control system troubleshooting to me. It wasn't, let's figure out if this port is open and this firewall is passing the traffic across it. It's, did the mouse or the rat chew the cable? This is the level of technical troubleshooting that we did, right? Lots of that's still around, especially when you drill down into the lower layers of the control system. So let's talk a little bit about some terminology. You'll hear control system engineers talk about the loop, the control loop, right? So usually when you're connecting a control system up, or you're doing that design, you have the intent to measure something and you have the intent to manipulate something, right? It's like the shower, right? Take a shower in the hotel room this morning, the water's coming out, it's too hot, you turn the valve, right? It's too cold, you turn the valve the other way. Well, you're the control system in that particular piece, right? So your skin is measuring the temperature and you're adjusting the valve. Well, that's what the control system does, right? So you have a suite of sensors on one side that are wired up to inputs into the control system. The control system is measuring voltage, current, frequency, all kinds of different electrical properties depending upon the sensor, performing some calculations in the middle, and then sending electrical signals out to what we would call final control elements, control valves, variable speed motors and pumps, damper positions, right? So you're moving a big arm on a damper to adjust the air into a boiler or something like that. That entire process is called the loop. And there's a lot of tweaking and a lot of opportunity to introduce error. There's a lot of opportunity to introduce latency or timing challenges with when the sensor is sending its signal versus when the actuator is making its moves. And more of those final control elements and the sensors out in the field are becoming intelligent. Remember, at one time, when even not that long ago, when I started, that was a pneumatic, that was air pressure, right? The sensor was changing air pressure. Then it got to electronic, where it was changing the voltage or current. Now it's sometimes sending a digital signal across some type of bus architecture. And a lot of times in an older facility, you'll have all of those operating at the same time in different areas of a plant. So lots of diversity, I guess, if you wanted to use that term. So in the electronic era, in the pneumatic era, we had defined pressures that meant what the signal levels were. So 0% signal from a transmitter was typically 3 psi. 100% signal from that same transmitter was 15 psi. So the system adjusted the pressure between those points, and based on where it was, you could calculate what the given temperature, what the given pressure, what the given flow was. Well, the corollary to that in a current loop became 4 to 20 milliamps. So in a loop, we used current because then you could detect if the wire got broken. If you used voltage and you had 0 volts be the 0% signal, if the wire got broken, the control system would just say, oh, well, it's just reading 0. In a 4 to 20 milliamp system, if the system has 0 in it, it means there's a fault or a break. You can also borrow some of the power in that 4 milliamps to power your instrument. So most of these instruments don't have separate power supplies, right? They glean the power off of that 4 milliamp signal going around in the circle. So 4 milliamps is your 0, 20 is your 100%. And if you're a control engineer, you have 250 ohm resistors falling out of your pocket everywhere, because if you run 20 milliamps through 250 ohms, you get 5 volts. So you get that voltage drop across that resistor that becomes your signal into your industrial control system, right? The important takeaway, I think, though, is when you look at these individual sensors, you could have hundreds of this given type of transmitter. Pick any one of your top vendors, and you could have a pressure transmitter, say, that reads a common pressure range like 0 to 100 psi on air pressure in a plant. You might have 100 of those. Okay, so now there's a vulnerability that comes out in that particular transmitter. Are all 100 of those in the same type of application? Some of them are probably just displaying a number on the wall or on a screen somewhere. Others might be a highly critical safety trip. And what kind of documentation do you have in place within your facility to be able to differentiate what their jobs or what their tasks are, so that you can prioritize maybe which ones you have to patch first, or which ones you should be putting more attention to in your security planning. Here's where it all starts to get cyber enriched. We bring all of those sensors and all of those final control elements and all of those PLCs and all of those distributed control system pieces into this control room. Typically the control room has another room that sits right beside it. We called that the rack room because it was racks full of equipment, right? This is where everything terminates. This is where all of these connectors come in. This is where all these networks live. And this is where the humans interface with the system, right? In the old acronyms, we used to call this the MMI, the man-machine interface. That was updated, thankfully, a couple decades ago. And we now call that the human-machine interface, right? The HMI. So you hear this term HMI. Where did it come from? Well, that's where the human sits down and interfaces with the control system. This is also where any alarms get generated, right? If you've ever walked into one of these control rooms, you probably hear things buzzing and beeping and blaring all the time. We were having a conversation last night over beers about alarm management. And one of my first jobs as a control system engineer, you go to a plant, you start up a greenfield control system, and there used to be a dot matrix printer or a line printer that sat there and spewed out the alarms. You'd go through the stack, literally the stack of printouts that printer generated overnight with a highlighter and say, okay, FI 6748 was in alarm 600 times last night. We should go look at the settings on that one, right? Thankfully now we've got some mechanisms to port that into databases and into spreadsheets, and we can prioritize those alarms, right? And get a better handle on it. It's not only the operator that interfaces with the system in this environment. This is also more or less the environment where the engineers or the technicians interface with the system. Probably a modern control loop, just one measurement, temperature to the actual controller, to the valve that's changing the steam flow, has potentially hundreds of different configuration adjustments or settings just for that one function. And the engineer's job is to go in and make sure that those are all consistent, that they're all performing the task that needs to be done, in this case controlling the temperature, and keeping track of all of them. You want to talk about a system documentation or change management type of environment. People talk about the difficulty of keeping track of what the firewall rules are or something like that. Try walking into a medium-sized plant that has 100,000 loops, and each one has hundreds of configuration settings. And then do that in an industry that has strict regulatory oversight like pharmaceutical. Changing any one of those adjustments could require you to go back and revalidate the system with the FDA and have to go through a complete change review to do, you know. So there are systems and mechanisms to handle these kinds of change management scenarios, right? But again, if you're walking into, you know, one of these kind of facilities from a security perspective and you don't understand all those nuances behind it, you can easily pay attention to the wrong parts of the control system, right? So now let's talk a little bit about networking. Dale's going to go into much more detail, but I wanted to introduce, you know, the Perdue model, this concept of a layered defense in depth type of networking approach. There's some discussion about the longevity of this particular model, but for the purposes of today, I think we'll stick with it. So if you look at a system like I just described with hundreds of thousands of potential loops and sensors and everything, you have to break them up into some type of order, or else you would just have chaos. So typically the industry has developed a way to describe in a tiered hierarchy where the device lives, right? And I think that if you can have the takeaway that the lowest level of devices, the individual sensors or the individual valves, live in this, you know, level 1 and 0 area, and that as you go up, you're aggregating more of them into the system. So you would have individual sort of I/O racks, input-output racks, where you're wiring dozens maybe of these things together. And then those little input-output subsystems get networked together through a digital bus like Foundation Field Bus or Profibus or something like that to go to a controller. And that controller may have, say, several hundred or several thousand control points in it. And then you have dozens of those controllers that are networked together across perhaps a high-speed redundant Ethernet backbone that runs through the plant. And then those controllers get networked once again or collated once again to go for the interfaces to the business system side of the house, right, through your demilitarized zones. Typically, that's the way you'll see most things laid out. And one of the things that I had to do, I walked into the job in the late 90s in the particular pulp and paper installation I was in. Completely flat network. Stuff everywhere. You had the email that the admin person for the boss, his or her computer sitting on the same network segment as, you know, the PLC that was controlling the high-speed slitter off the back end of the paper machine or something. And so we went through and basically segmented into, and I chose to do that by vendor. There's different ways to do it, but I found it much easier to group like vendor equipment together. That way the vendors were a lot happier when you called them and asked them questions and there wasn't other vendors' stuff on their network. Anyway, this is a key concept. This networking layers and networking model. And most of the security debate or discussion comes around where do you interconnect? At what point do you interconnect into the system? And some of the things like IoT are starting to throw a monkey wrench into this because now you've got all these field devices or sensors that are at the bottom of this hierarchy that are being brought in at a cloud level above everything. I think Brian Owen's is going to talk about that later on today. So I talked about this a little bit already with regards to the topology of a typical distributed control system. If you think about how you've got this hierarchical system of hundreds or thousands of devices coming up into controllers and then coming up into one, you know, sort of master configuration database, what we would call the Engineering Workstation, you can see that that would be a juicy target from a attacker perspective, right? Because that's where all of these settings are stored. that's where all of the change control exists for the entire system, right? And so what happens if those pieces become unavailable, right? Are there redundancy concerns? Are there backup concerns? It's still amazing to me. We'll talk to people about, where are your backups? So you think about some of these installations, if they have 100,000 of these temperature transmitter type sensors, where do you keep do you have like an individual file for each one of those? That if somebody runs over one with a forklift, how do you put the programming back into it? Many different structures, right? If you go a typical distributed control system sort of technology, the system will actually reconfigure those devices for you as you bring new ones in. If you go with a sort of integrated system that has many different vendors sort of tied together, you can have a lot of onus put upon the control system engineer to make that tracking happen, right? And to make sure you've got those kinds of backups available. Now let's talk about, if you go back to the 4 to 20 milliamp conversation we had with that current loop, right? So you had this twisted pair of wires that ran from the transmitter to the system. Here, I'm going to say 15 plus years ago probably, people started to say, I bet we could superimpose a digital signal on top of that and get more information out of these devices or push more information to these devices. And this is where you get terms like HART, which don't try to make me remember what that acronym stands for. But you essentially take that electrical signal that's been there for decades, that's measuring the temperature, communicating the temperature from the transmitter up to the system, and you superimpose a serial protocol on top of it. So now that transmitter can tell the control system things like what's its minimum span value or what's its maximum value. So what is the range? It can send things like health information, like, well, I'm a pressure transmitter, but I had really high frequency noise on the sense line for my entire life, and now it seems like I don't have that same amount of high frequency noise. Maybe my sense line is plugged, the measurement that I'm trying to measure. So all kinds of really good things that you can get out of these transmitters and send out to these valves. But now you have another digital component in there that you have to manage. And there's actually quite a bit of discussion in the community right now about, are there cyber implications to some of these? And I would say yes. So for example, you can have a sensor that's connected to a safety instrumented system that's a highly critical shutdown system, and if it's communicating digitally, there are devices that you can sort of tap onto that digital signal to peel it off into another engineering workstation environment to calibrate or check the performance of that. Well, now you've just basically bypassed that entire Perdue model from you could have all the firewalls you want that were in the top layers, all the security that you want, and if you've bypassed it down at this very low level and it's not documented properly, you might have an issue from a security perspective. Lots of configuration management. Change management is probably one of the biggest challenges that a controls person has these days. Just keeping track of all these devices, what's inside them, and how to restore all that information if it fails. So let's talk a little bit about different topologies or terminologies. So I'm a DCS engineer. That's basically where I cut my teeth. Distributed control systems. Typically were used in wet process type of environments that had a lot of analog measurements, a lot of temperatures, pressures, things like that. The programmable logic controller came out of the automotive industry. Lots of is this position in place in this tool, right? Is this conveyor belt that is the assembly line in an automotive factory, is it moving and is it in the right location? So lots of on-off types of things. And typically higher speed processing than some of the distributed control system applications. This area has really, what I would say, diversified from a vendor perspective. You used to have one or two, maybe half a dozen big vendors around the world that most of this stuff came from. You're seeing a ton of kind of Ethernet, internet enabled data gathering devices now that loosely fit into the PLC category, right? You can go to a lot of different websites and for under $50 buy something with some I/O. You know, a chassis that had a decent amount of I/O in it was tens of thousands of dollars when I was starting in this industry, right? But all these definitions kind of are getting blurred a little bit. It's interesting to note that, you know, in the programmable logic controller world, the programming methodology that they originally used was very similar to electrical wiring diagrams, right? This concept they call ladder logic. And that was so that the electricians in these factories that were used to having a whole board full of electromechanical relays used to build your logic about how you wired these relays together, right? Push button here goes to the coil of the relay, it'll close the relay to energize the pump, you know, the motor that's on the pump. You could wire your interlocks in, but if you wanted to change your logic, you had to physically change the wiring that were in those relays. So they basically took the nomenclature, the diagrams that the electrical community used, and they made that the programming language. It looks a little foreign to most computer programmers that are coming out of university today, right? They go, ooh, that's different. And many of the PLCs now, you can interact with them in different ways, right? So they have object-oriented or layered structured programming tools to be able to view the logic in different ways. But you'll see on the factory floor, a lot of the ladder logic still gets used. SCADA, or SCADA, if you're from down under, supervisory control and data acquisition. So the best way to think about this type of implementation is distributed control system, programmable logic controller inside the fence, right? So you have a chain link fence around a factory or around a pumping installation. Most of that control is inside the fence. SCADA is outside of the fence, or many miles between the fences. So typically, the descriptor that I like to use is these are systems that have large geographic installations. So think things like the electrical grid, think things like pipelines, right? So if you have a pipeline installation, every X number of miles, you've got a compressor station or a pumping station. Well, each one of those will have some localized controls in it, but they might all be connected back to a master control room in a different city that's in a different state or even in a different country. There's somebody that's operating or dispatching that system from many, many, many miles away. Okay? You'll also see backup implementations. So SCADA tends to have relatively slow communications requirements compared to like something that's running a really high-speed processing machine. You know, so if you've seen on television any of the sort of discrete packaging where they're running, 5,000 bottles of beer an hour or a minute through this machine, right? They're flying right along. Well, if you're scanning the barcode on each and every one of those, or you're counting them, or you're measuring the level of liquid in each one of those bottles as it's going by, you're doing those calculations pretty quick. In a SCADA system, you might be measuring the level of a water reservoir, that the reservoir is 100 acres, right? So it's not going to move very fast. That doesn't mean it's not critical that measurement comes in, right? But it just means that different communications properties. Lots of wide area network stuff, lots of cellular, lots of microwave, lots of satellite, lots of different communications protocols here. So let's talk a little bit about specific terminology inside of the control loop a little bit. So go back to my basic sensor, controller, final control element. This is a pictorial diagram of a level control implementation, right? So you have a device inside a tank that's measuring the level inside of the tank, and you have a valve that's manipulating, in this case, the flow out of the tank. Very typical control loop, right? In this case, this is all in the field. The operator would have to go out to the actual tank to adjust the knob on the side of the controller to set the level. And if you notice from a terminology standpoint, the little lines, slashes on these indicate that that's a air pressure or pneumatic signal. You'll see different representations for electrical. So here's the same control function. Now this is with electronic controls, right? So this is how we start to use the process and instrumentation diagram, the P&ID. This is what engineers use to document and define what instruments are connected to what parts of the process, how are those pipes interconnected, what are their functions, how are they wired together, and in some cases how they're programmed. So some cases they'll document things like alarm settings. Quite often that gets done on a more detailed version that I don't go into, that's called a loop diagram. This is where you're first going to see the correlation of that tag name or point name. So if you're in the security world and you see these things like, LAH 5021, that level alarm high nomenclature, this is where those get defined, right? These are what gets defined per what that tag does. Lots of different things you have to think about if you've pulled all of this information together into your control system. And I don't think that we think about some of these things often enough, right? So it's not just the system and the system is running. There's all of these different configuration settings that we need to be aware of, that if they get tampered with, let's say, you could cause an engineered function to perform in a totally different way, right? There's things like if pressure goes up, then we want to close the valve. Well, if you just flip that one bit and say if pressure goes up, we want to open the valve, then you're going to get an out of control type of situation, right? And understanding each one of those bits inside of the system is often a big challenge for an attacker if they're trying to do something to manipulate the system into a dangerous position. So it's this concept of criticality and what does this individual piece of information do that's so important. I mentioned before that one of the first jobs that Mr. Byers sent me out on was this troubleshooting of this big data highway kind of implementation. Often these communications links can go between different pieces in the control system, right? So you've got a programmable logic controller on one end of the paper machine and another one on the other end, and they're talking to each other over serial communication, over Ethernet, over some communications medium. Unless you understand why they're talking and what they're talking about, you don't know how important that specific communications network is. And you could have two communications networks side by side that, cutting one is just it's not a really big deal. Or cutting the other one means all of a sudden you're in an emergency shutdown mode and you're blowing steam out of big steam pipes on the side of the building, right? Very difficult to try to assign a severity or criticality to unless you really dig into what that communication is used for. And I'll tell you, a lot of plants, they've just lumped stuff into the network for so many years that they've forgot. So everything's important, right? Because they actually don't know what's inside that pipe. A little bit of review. I talked about the distributed control system being more of a wet processing, analog. There can be some very complex mathematical control schemes here. Distributed control systems can have multivariable controls, fuzzy logic, model predictive controls. There's a ton of advanced math that goes on in some of these DCS applications for optimization. Programmable logic controllers, more of a discrete automation type of environment, although the vendors for both are cross-marketing into each other's territory, and these lines get blurry. And then SCADA, again, that geographical kind of separation. You've got systems that are many, many miles apart, coordinating or communicating what they're doing over, quite often, public communication networks, right? Okay, that is it, and I have 5 minutes for Q&A. So I went through some of that fairly quickly. Any questions on any particular piece? Sir.
A question on that last slide. I was furiously writing some notes and didn't quite get it to everything, but I think you were making a point about the difference between DCS being for wet processing, and then was it ICS for
Programmable logic
PLCs,
controller,
okay,
PLC.
thank you. Yeah.
And go ahead.
Well, so the question would be: is the implication that you're thinking that a vendor who's approaching the market should be perhaps focusing on one versus the other, as opposed to saying that they do both equally well?
It depends on the vendor, right? So some vendors tended to come from the distributed control system area. I would say that most of the DCS type of applications that I've been involved with, that one vendor has this sort of master configuration database that everything in the system is done by that vendor. In the programmable logic controller implementations, quite often you'll see each PLC individually configured. So you'll have maybe a dozen of these PLCs, but you as the engineer have to keep track of the configuration in each one and have to keep track of the inter-PLC communication. Like I said, it's becoming very blurry now, especially through mergers and acquisitions. Really big companies are buying, their competitors or complementary products, and so there's this whole automation control system, right? People are tending to blur the lines a little bit now. But good question. Any others? Otherwise, I'm gonna. Oh, go ahead. Yes. Wait for the mic. It's on video.
So for what you were talking about, configuration and change management, what have you seen as a trend in combining the, I'll say, OT config change management with an IT-based type of application, so IT or incident responders can get insight into those types of devices?
It's been attempted. I'll say that I haven't seen it be very successful in a lot of cases. Sometimes for plain inventory or asset inventory, then you can start to see the OT environment get defined and documented inside the overall IT change management system. But most of the, if not all, of those IT change management systems aren't granular enough to document all of the individual hundreds of settings or changes, right? And there are some pretty good OT-specific change management systems that will basically on a periodic basis or on an ad hoc basis capture the configurations out of all these devices, store them, snapshot them, compare them, and go, oh, by the way, because I used to get a report in the morning that said, but do you know that an electrician or a technician changed a setting in one of these things last night? And if you're not paying attention to that, you can easily get out of that change management. So I think that's an opportunity there. There's an opportunity for us to use the tools that we use in automation on the control system to help our IT brethren manage some of their infrastructure, because we're really good with data and historians and storing data like that. We should use some of those tools to help us manage our infrastructure, not just manage the process. It always confounded me that you could walk into a pharmaceutical plant that they knew every single change in a process safety management, PSM type of application. They knew every change in the system. Physical changes, we switched out this coupling. And because it was different than the coupling that was in there, they had to sign all these forms to document that coupling was different. But yet we don't know who walked into the rack room last night and moved this wire on this switch. We have the process there. We have the paperwork and the forms and the know-how for how to document that. We just need to turn it inward and like use it to keep our own system on track. One more, last question. And you, oh, over there. Let's pick you. Yes, you. Yeah, so here's the mic. Sorry to my other friends here. Go ahead.
And it may be answered later during the day. I'm just curious, for your last slide, how do you think IoT, the software-defined cloud, open source, all these things mess up that diagram or that slide?
They do mess it up. I'll say that other speakers are going to talk more about that. I think the biggest challenge that we have in the automation area is figuring out where to bring that data into the control environment or where to publish that data out to these cloud applications. And so if you think of it in kind of the what ISA 99 IEC 62443 is the zones and conduits model, right? Figure out the security for each area of your system and then figure out the security for each of the pieces going out. So a lot of IoT sort of implementations where you've got 100 of these sort of lick and stick sensors that are reporting back. The gateway piece that sort of consolidates that information, I think, is where you need to pay the most attention based on criticality. Okay, 0.
Nicely done. Nicely done. That was amazingly well done.